1 decade into cloud native, and this talk is going to be a little history back along that, and also looking forward to the future and what's going to come in the second decade. So to begin, I'm actually going to walk back about a decade to my first KubeCon in Copenhagen. This is me at our startup booth. Like every good startup, this one went out of business about 3 months after this picture was taken. And I was then on to my second cloud native startup about 9 months into my career. But what I really did take away from KubeCon in Copenhagen was there was a lot of energy around this thing called Kubernetes. And when I went to the conference, I thought Kubernetes was just a really nice island in Greece. Unfortunately, somebody put me in front of the command line and said, you're going to set up a Kubernetes cluster, and I quickly realized it was not going to be a fun vacation. It took me about 8 hours to set up a Kubernetes cluster on my Windows laptop in Kubernetes 1.8. But the thing that I did take away from this conference, I think there was 2 big things for me. So the first one was this slide, and it's going even back another decade, kind of tracing the evolution from hardware to cloud native. You know, from when we're actually racking and stacking boxes to more virtualization with VMware, infrastructure as a service, and the beginning of cloud with AWS, PaaS, and the beginning of the open source movement, right? That's kind of the evolution of technology from the physical hardware boxes to cloud native that got us to where we were in 2015. But the problem that cloud native was trying to solve, right, is instead of having to go and take people and plug in servers, you know, redo IP addresses and manage individual applications, we needed a way to orchestrate that. There was too much data, you know, we had ephemeral containers, IPs were changing all the time. Like what originally took a team of people, you can now automate with Kubernetes. And that's what made cloud native so powerful, was this whole new paradigm of being able to automate away toil for teams. Now, the second thing I took away from that KubeCon was a keynote from this person named Simon Wardley. And the thing that he's famous for is his Wardley Maps. And kind of the idea behind this is giving an evolution of technology on a map. And so being able to trace the evolution of things rather than, you know, telling a story about like, oh, I think this thing is happening. It's talking about the evolution of technology from the genesis, the idea, all the way to when it becomes a commodity, like light and electricity is now, and looking at it on the value chain from invisible to visible. So I kind of copied his slide from this, and he's kind of talking about where things were in 2017, where you have your application is very visible to your business and your end user, and down at the bottom you have cloud is like, you know, more of a commodity, and various other pieces of your technology stack in between, from genesis to custom built the product to commodity, and more or less visible to you as a business and to you as your end customers. Now, having hindsight, we can kind of look at what he was thinking at the time and maybe think it's kind of funny now, right? Like the big thing here that I think is kind of funny is like serverless. He thought it was going to be this next big thing that's going to kind of become a commodity in how we run all of our infrastructure. I think probably if you're in your room, you don't think that's true, right? We're at like Kubernetes community days. But you know, the thing that he was saying is, you know, as technologies change and evolve, like products become commodities, new practices evolve out of this. So at the time, right, the good architectural practice was like ITIL, talking about like mean time to recovery, but then this whole DevOps thing came along, and that's going away. And then, you know, cloud native allowed a new architectural practice that allowed us to look at, okay, like how can we redesign our applications when we take cloud native principles behind it? And that's kind of like the new tribe that he was saying was forming at the time, and this is kind of the moment to codify some of that and bring it around. And so what kind of like were those ideas that we were talking about in 2015, 2017? What did cloud native actually bring to us? Well, a lot of things were, taking our monoliths, breaking them up to independent microservices that they could be worked on by separate teams and used independently. Moving from, like infrastructure where each of our servers is named after your favorite Star Trek character or your favorite Star Wars character into more declare APIs, something that you can do repeatedly, moving from imperative infrastructure to something that's more declarative, and moving from tightly coupled systems where everything's all together into more loosely coupled things that can be that can work together. But I think this is a lot of the things that you'll find in the cloud native definition if you go to the CNCF website today. But one of the things that we didn't think about, and I don't think has really changed that much in the last decade, is kind of how we actually control this infrastructure. I think we've gone from centralized control to centralized control. Like, not really that much has changed here. And you may be asking, what do I mean by centralized control? So let me tell you a story from Trip.com, their user of Cilium. This is the slides from the talk that they gave at KubeCon China in 2023. And stop me if you've heard this story before. So Trip.com, if you're not familiar with them, is a large travel services provider. They run hundreds of Kubernetes clusters around the world with thousands of nodes. Obviously, running at that scale and complexity comes with a lot of challenges. For instance, sometimes things go wrong in your API server, and it starts to go on fire. And what do you think happened next? The Cilium agents on your nodes reach out to the API server and say, hey, what should I be doing right now? Well, obviously that fails. So your agents start crashing. All of a sudden your network isn't working. You're trying to list and watch to the API server, to the etcd, and now your etcd is crashing, right? Who doesn't love a crash loop back off? Right? And so this is the thing, is we're calling back to these centralized services as the scale, complexity, and dynamicism of our infrastructure continues to increase. So that's the problem with centralized control. And I think that's what we're really starting to see as we go into the second decade of cloud native. We're starting to see it break down, right? What we just saw is we had an overloaded system, so we start to drop the signals that we have. The calls come back, or the calls don't come back, right? And as we start dropping calls, we're making more requests to these services, and the data transfer and require larger pipelines, right? As we're increasing the pipelines to be able to feed everything back to our centralized servers controlling these things, we need to ship and store more data. Our etcd cluster increases, the complexity of our etcd deployment increases. This leads to increasing infrastructure costs. As the infrastructure goes larger, right, there's more latency between all the different loosely coupled services, so the decisions become late or don't come back at all. You're suddenly in this seemingly never-ending loop, and because of that, Kubernetes is eventually consistent, right? It's not always consistent. So if things start to get delayed, it starts to lose the context of what the actual state of the system is, right? Everything's eventually consistent to nothing. So you really become divorced from these real conditions. And that's where this centralized control really starts to break down, because at the end of the day, it's kind of like the bureaucracy is expanding to meet the needs of the expanding bureaucracy. You're just adding more and more control, but at some point, it doesn't quite work out. So as we move into the second decade of cloud native, I think what we need to do is to move from this centralized model to a model of more distributed intelligence, where we can move the decisions that we're making about our dynamic infrastructure a lot closer to the data that actually matters. And so what I'm going to do in the second part of this presentation is walk you through a couple examples in networking, observability, and security about how we're doing this, being able to move the decisions actually closer to the data. So I'm going to start with networking. So one of the favorite things as a maintainer of the Cilium project is to talk about the sidecar-less service mesh. Right? So this is where you have, the traditional model was to have a sidecar right next to your application in the pod. And this led to a lot of overhead, because suddenly you have to go back and forth through the Linux networking stack multiple times. right? Cilium is able to take the data right off of the socket and redirect it. It's moving, okay, I know this packet is coming out of my application, I know where it needs to go, right? It's moving the actual decision of where to move that data, or that packet, a lot closer to the actual source. And so we did a lot of research into this, and so that's why Cilium built like the original sidecar-less service mesh by limiting these multiple traverses through the Linux networking stack. And you can see from the graphs here and a lot of other things, and you've seen kind of the transition of the industry from regular service mesh with a sidecar to, I think most of them are moving towards a sidecar-less model because of the advantages you get by removing that extra overhead of going through multiple times. We're also seeing this in places for like DDoS mitigation. Now, this example actually comes from Cloudflare. So rather than using like IP table rules to try to decide, should we drop this traffic because it's a DDoS type of attack, right? You have to come off of the hardware NIC into Linux kernel networking stack. You have to check whether that's a bad IP that you want to be able to drop the traffic. And by that time, you're already spending a lot of CPU cycles by actually reading it into the, from kernel space into user space. What they're instead able to do is to implement the logic with eBPF and XDP right actually into the hardware, into the NIC. So as it's coming off of the wire into the hardware, they can make the decision right there whether to drop the traffic or not. And this actually led Cloudflare, you can go on their blog, to auto-mitigate a 3.8 terabit per second DDoS attack. Right? This kind of scale and complexity that we're seeing in the world now requires a new way of thinking about infrastructure, being able to move the decision-making not way into user space, we're moving it almost directly onto the wire. And we're also seeing this in the Cilium project too. I think this graph here on the bottom is one of my favorite ones that I've heard about. This is Cilium, a Czech company, and they switched from an IPVS based load balancer to an eBPF one based on Cilium. And when they put it in production, they actually thought that they broke their system because the CPU was so low. And so because they were able to make better decisions with XDP and eBPF, they're able to save a lot of CPU, save a lot of money, save a lot of complexity for their company. So that's in networking. Next part is observability. So I think a lot of people are familiar with the ever-increasing observability bill, right? Your application, is accessing things, talking to different applications, you're collecting that telemetry, exporting it to your observability or SIM tool of choice. Maybe you're doing some filtering there, but you have an ever-growing pile of observability data that may or may not actually be providing you any value, but is definitely costing you a lot in terms of increased infrastructure. Right, so rather than shipping it to some centralized place so that it kind of rot and die there, what if instead we could be smarter about the data that we're actually collecting? So being able to filter the data right in the kernel, like the Linux kernel, and decide what data we actually want to export for future things. And being a lot smarter about it, right? We don't need everything, we just need the signals that we want. And so Tetragon, another sub-project under the Cilium project, actually does this. So these are two benchmarks one is of monitoring file reads, and the other is looking at kind of the CPU usage of doing file reads. And what we found is that it's actually a lot more efficient to be able to choose what data you actually want to do and decide at the point where the data is actually generated rather than way down the line in some centralized system. So this saves you the CPU overhead of shipping the data and processing the data too. And so what does that mean for you? Rather than having to spend all of your money to export the data and store the data and maybe filter it later, you can export a lot more data and have a lot more control on the fire hose of observability data. Being able to actually look at the data closer to the source too is actually a real big benefit for people too. So the last sub-project under Cilium is the Hubble project, and that does network observability. And it's collecting with eBPF the information right off the wire of what's actually happening in your network. So, and I've had a lot of users of the project talk to me and say, this is my favorite part of the project because it allows us to diagnose what would have taken 2 engineers 2 days in about 3 seconds. And right, that's an easy trade-off to explain to your boss. Hey, look, we're saving 2 days of engineering time because we have data that's generated a lot closer to the source. And then the last part I'd like to talk to you about is on the security side. So in terms of runtime enforcement, what a lot of tools do right now is they look at what's actually happening in your application or your infrastructure, they hook into it, and when something bad happens or a malicious actor comes in, they're going to export the event to an agent, which will go to your SIM, which maybe then will do an enforcement type thing and block it, right? But that's a really big lag, especially if somebody needs to go into a dashboard and actually look like, hey, is this an alert that we should actually care about, or is this an alert that we don't need to care about? And once we actually have that alert, what can we actually do about it? What if instead we actually kind of have all that context in the kernel where it's actually happening? So if an application is making access, for instance, to a passwords file that it shouldn't be doing, well, the data's all right there. You can make the decision to block it, like in the kernel, right? So rather than going all the way out to user space in your SIM, and then maybe to a human to review the data, you already know it shouldn't be doing that, so why not just block it directly in the kernel and kind of short circuit this whole path, right? So this allows you to have a more secure system because you have better context and there's a less delay between when the action's happening and when you can stop it too. And just like in observability, we can see like the same thing. If we try to export too many security relevant, alerts, what can happen is we can overwhelm the system. So we've seen this before as you're trying to trace all the things that are happening on your system, and you're saying, okay, we should watch out for all of these things, and we need to export all of these events. Well, you can actually have a DDoS type of event too, where you're trying to export all these events and your system will run out of resources. The attackers can starve your system of resources so you'll miss the real attack, right? So rather than trying to export all of that and then filter it, why don't we filter it and only look at the specific things that we want to, right? Find the needle in the haystack rather than trying to dig through the whole haystack. So kind of summarizing these 3 different use cases in networking, observability, and security, like what we're going to be doing in the next decade for cloud native is adding distributed intelligence into our distributed computing. So that's going to be analyzing information in the kernel, filtering it earlier, and being able to act instantly on that data. So that's a summary of what I've seen happen in the last decade of cloud native. And what I promised at the beginning was looking forward to cloud native's second decade. So since I made fun of Simon Wardley at the beginning at his graph, I'm going to make some of my own predictions, and then maybe in 10 years we can laugh at what I said on the stage today. So this is where I would have kind of put things in 2015, right? You still have your application as very visible. We saw cloud native as the emerging architectural practice. We had some old coding practices. Kubernetes was somewhere between custom built and product. Things like Cilium were still like very custom built, and eBPF was something that only the hyperscales were even looking at. And as we progressed along in the past decade of cloud native, I think what we've kind of seen is cloud has gone to almost a complete commodity. A lot of people have taken on cloud native practices that I talked about at the beginning, right? That's why we're all here today, gathered at Dutch Cloud Native Day. Kubernetes has become pretty commonplace across a lot of infrastructure. It's moving towards a product, closer to a commodity across all these different cloud providers. There's hundreds of different clouds that you can now spin up a Kubernetes cluster on. projects like Cilium are also moving from kind of this custom-built solution on this crazy new technology, eBPF, into a product that's become the de facto standard for Kubernetes. And people are really learning how to use eBPF to do different things to their application. So if we map kind of all those changes today, we kind of see this new map. And maybe cloud native is becoming the new legacy. I know that may be kind of wild or mean to say it, Dutch Cloud Native Day, but a decade in, that's a really long time. And if I'm going to be standing up here on the stage in a decade, I don't know if I'm going to be talking about cloud native. What is that emerging architectural practice that's going to be what people are talking about in a decade from now? And if you ask me what the second decade is going to be, it's really going to be infusing that intelligence into our infrastructure so that we can look at things right when the data is generated, so that we can analyze at the source, so that we can act instantly. I think the way that we're going to be doing that is with eBPF, because it allows us to programmatically extend the Linux kernel across networking, observability, runtime security, policy enforcement, tracing and profiling, scheduling, interactions with external devices, and so many more use cases. And that's what makes eBPF really exciting for me, and why I think it's going to be so important for the next decade of cloud native. So with that, thank you, and I have time for any questions.
Thank you, Bill. Amazing. Do we have any questions for Bill?